Okay, now in the last class, okay, we basically boiled down everything into a major two numbers. Okay, the first one was L over D, and the second one was the Sommerfeld characteristic number. And we said that while this is a geometrical number, and if you are not designing, usually the geometry is known. And the S number, which is obtained from this equation, again, if you are not doing design, if you are analyzing, then you will see that the dimension R and C would reasonably be known. If this is not a design problem, then why you shouldn't know the viscosity? Of course, you know it. So in this problem, we realized that one value which was unknown, which is the pressure. So we calculated the pressure, and it turns out to be 222 psi. We took that pressure value, plug it in the equation in order to get S, which turns out to be 0.135. Okay, we calculated L over D, and it turns out to be 1. And that's it. The next is to have most of the figures, okay, being characterized by these two values. So whenever you have L over D and you know S, the bearing characteristic number, then you can somehow hit the y-axis on the right and the left, like here. We can see that we have H0 over C, and in here we have epsilon. And from these values, you can find, you know, the status or the condition or the measurement of the bearing. Now, if I remember particularly, we stopped around here. Just to remind you, this is another curve which require S from one side, L over D from the other side, and here we have a ratio which is C. Is it C? No, R over C. So it's a dimensionless ratio, R over CF. And of course, if you know this from the y-axis and you know these values, you can divide and multiply to achieve F. Or maybe you know F and you want to know C or something else. So I would imagine, ya shabab, that you might encounter a problem where maybe you know this ratio, and then your question would be, which one of these curves is the right one if you have designing? So maybe you want to pick L over D, a ratio L over D, and then decide about S, and then trial and error and so on. But ultimately, you want to arrive to this L over D and S. Otherwise, you cannot move on with these charts. So if you recall here, when we determined the friction, we were able to find the frictional torque, which we can take and apply into a power equation to find how much we're losing in horsepower or in PTU per second, which is a unit, you know, mostly used in heating system, like cooling, heating, which is an essential part of the journal bearing analysis, and we will see that in this is the same problem. We are asked for L over D equals to 1 and a ratio, if you remember, which was 0.135 S, to find what? This, the flow rate, Q divided, a dimensionless flow rate, which is Q divided by R, C, and L. Again, if you know this ratio, you can multiply these to find the Q. Good? find the Q, you can find the QS over Q. Because again, this is L over D, and this is the S number, and then you can find this ratio, and by knowing Q, you can multiply this by the Q by the ratio in order to find the QS. QS is the side flow, which we are going to discuss in a bit. Now, the next part is the pressure, the maximum pressure. And we told you that if we have a journal bearing like this, the distribution goes in a polar manner like this, where we have a point, the pressure will become maximum, right? Now, that can be obtained from another chart which relate P to P maximum. So again, if you know the S value and you know L over D, you can go ahead and find this ratio. From this ratio, you can calculate P max. And if you see here, while we applied a pressure of 200, the projected pressure from the load is 222 psi, the maximum pressure reached to 529. Okay, now you remember I told you about two angles. The first one is the angle at which this pressure is going to be obtained, or it's going to occur. This is theta P max. And remember, Shabab, this is very interesting information. And for an engineer, these details are very crucial. Like, let me give you a scenario, a virtual scenario here. If you are an engineer and you're working in a workshop and there are technicians, okay, without undermining anybody here, but this is the rule of an engineer. You know that there is an angle which can be estimated, and it can guide you on the surface of the bushing, the lower part of the bearing, where to look. So in this problem, we know that P maximum is about 18.5 degrees. So if the bearing is like this, you will come here and you say, okay, at angle 18.5, I know that this spot, this is the location of the maximum pressure. So if there is an inspection going for whatever reason, and let's say you said, you know what, there is something wrong going and we need to inspect this under the microscope. You know, when you go to the microscope, it looks funny. I mean, interesting. Wow, we're going to look at the microscope. But few minutes, ya shabab, you never used a scanning electron microscope. It is so upsetting that the second you sit on that chair, you put the little sample inside this chamber, which is, vacuum, and then you bring the gun which shoots electrons, and then the electron scatters, and then they get received by the detector, and you see the image. You say, wow, I'm gonna have the best day here. But then the more you magnify, right? Electron microscope can magnify up to 1 million times. Well, don't be happy. If you magnify 1 million times, it means that you will move in microns. And in microns, a piece like this, you can spend a year on it scanning it, because you can look everywhere. A micron is too tiny, so you just move, you always see things. So what I'm trying to say here is that you know that there is a region over here where the pressure is maximum. So you may want to focus on that region. Yeah, if you went to an industry one day and an operation technician or whoever brought you a journal bearing and say, look, everything is shiny except this place. There is a rubbing. Why? Why only that point? Why not everywhere? You know the answer. It could be the location of the maximum pressure. It could be somewhere else. You know where is the somewhere else? Because to our surprise, when Raimondi and Royd did their analysis, they realized something very interesting, which is at a point after this. You see here, this angle, let me make it in green. This angle from here to there, okay? So I think I ruined this graph. So just for the sake of your understanding, let me quickly redraw it again. So this is the journal bearing. And we said I'm going to make it in blue. This is 18.5. So this is the location of P maximum. Okay. There is another angle over here, which is called P theta 0. This angle is measured 75 degrees. What about that angle? This is the angle, ya shabab, where the pressure, you know what Raimondi did and Royd, when they analyzed the pressure distribution, they realized that there is a point after which the pressure becomes negative. Now look, what is interesting here is, I am pretty sure that when you hear it, you say, okay, okay, but think of it carefully. What does a negative pressure mean? Anyone? I'm not talking about negative energy, huh? Like physicists. I'm talking about a negative pressure. How?
Negative pressure?
Maybe when things are sucked in.
Okay, that's a reasonable thinking.
Like compressed.
Well, a pressure is always, have you seen a pressure which is doing tension? A pressure is a pressure. It's always compressing. So what is a negative pressure?
Would be probably creating a vacuum instead of applying force as a pressure, is creating a vacuum.
It's just
Anybody?
on direction. I don't know. Maybe.
Well, we do this trick in finite element, Shabab. We go to the software. You can do it in SolidWorks. If you want to apply a distributed load like a tension, you put a negative pressure. A pressure, if you say 100 megapascal pressure, it is negative. It is already in the direction sense. It is already compressing. But we put it as an absolute value. We say a pressure of 500 megapascal. What would you expect? You are sitting here and there is a pressure coming on you, 500 megapascal. Now, a negative pressure is opposite. So it has to be tension. Now, while this thing does, I mean, how would you take a fluid and apply tension to it? How? Go try it. I mean, just take a bottle of water and take the water and then try to apply a tension load in the water. So what they did, they said, well, the equation, just like when an equation gives you infinity, it's trying to tell you, oh, the value is going too much. I don't know what's going on, but it's too much. And here, the negative of pressure is actually a tension, and a tension, instead of making it this mysterious, what does a tension to fluid means? They actually thought that the equation is trying to tell them that in real life, this is a point when the pressure rupture. I mean, when the filament rupture. It's like the pressure here and there, all of a sudden you have a rupture in that filament. Now, that rupture might raise a question on your head. Does that mean that there is no oil? Instantaneously, of course. Is there a chance that there is a metal-to-metal contact? What is the effect and what's so? So there isn't too much detail about this. And since there isn't, I mean, we're not just going to go and put on too much material on you. But I want you to understand, for your sake, that this angle is where this rupture is expected. And to me, if I am an engineer, I would probably look at the three angles. Don't mix it up. We have another angle which is called phi. So if I am an engineer, I will only look at these three angles. The phi belongs to the location where H0 is obtained or achieved. That's the location of the minimal clearance, and the chances of metal to metal contact might be there. There is also the location of maximum pressure, and there is also the location of the rupture. So three important locations. And just to remind you that this is the maximum, this is theta P0, and there are two curves, one for each. The one with solid marker is for the maximum, and the one with open marker for 0. Okay? Now, what is important is that while we are speaking here about the fluid, we should understand, I mean, the lubricant, that this is a system. Yeah, this is a whole system. And what is important here is to know that while we are supplying, I mean, we spoke about this in the beginning. We said journal bearing have this thin film separating the two, the journal and the bearing, from being in touch. And there is a pressure, there is a friction, so there is an elevated temperature. That heat needs to be taken out. And we told you that in most cases, there is a kind of complementary system with the pump or the compressor to cool down that oil. Now, as engineers, again, we don't underestimate things. We don't just go and say, if I need to push the flow, maybe too slow will overheat the oil. And how much fast should I push it? Yeah, how much? And if you remember, Timberler recommendation for design was to maintain the temperature to below 121. So again, we don't make guesses, ya shabab. We don't go trial and error. We don't waste energy, resources, money by trying. Let's try this. Maybe no. Let's try that. No. We make them as much as possible into an at least approximate relation. So here, we're assuming that we have the journal bearing right there. And this is the journal, and this one is the bushing of the bearing. So in a simple term, we're going to say that this is the supply. We're supplying the oil, just like what Reynolds imagined. There is a flow. That flow can have two characteristics: the flow rate, Q, in a volume per second, per minute, whatever, a temperature T1. Now, when the flow goes, we said that, some part of this is going to go on the other side. So for that reason, this is the return oil, which will go to the cooling unit, whatever, or it will circulate again, as we are going to discuss later. So here, this flow is not exactly the same flow that gets in. There is what we call it a leaking. A leaking means the oil is also coming from the side. So it's coming this way and it's going on the other way. You can't prevent this. So we call this one the end leaking. So this one is actually QS. That's the side flow. So if the side flow gets out from here, what is the reminder, ya shabab? Q minus QS will go from the other side, right? So, and in here, the side flow will have a temperature, which is T1 plus delta T over 2. What is this? We're averaging the temperature between the in and out and taking it out. And in here, we have a temperature T1 plus whatever, an increase in temperature, okay? So if you look at this, we have the volumetric oil flow, which is coming into the bearing, and it is measured in inches cubed per second, which is equivalent to meter cube per second. And then we have the side flow leakage rate going to the sum. The sum, ya shabab, is like a little tiny pool, a place where the oil accumulates, okay? If you want to have the meaning of this word, you know, more tangible, you can search it in Google Translate. There are multiple translation for what the sum means. And then we have T1, which is the inlet temperature. Delta T is the rise of the temperature. Rho is the lubricant density. CP is the specific heat. J is the Julian heat equivalent, which is in pound force per BTU, and then the heat rate. Now, what happened is this. I'm not going to go over the derivation for this. What you should understand is that when we arrive to this equation by, you know, deriving the whole relation between the heat and the flow, we came up with this equation. And in this equation, we have the variable J, the variable rho, and the variable CP. All of these are the same for petroleum lubricant. So we say, okay, let's make our life a little bit easy. Since most of the time we're talking about oil lubrication, which is a petroleum lubricant, then what are the values for CP in general for oil or petroleum lubricant? The density in pound mass, not pound force, per volume, unit volume, which is inch cube, is 0.0311, which is an equivalent of 862 kilogram per meter cube, CP and J. By taking these, plugging them in here, we can get the relation which relates, as you see, the flow, the side flow, the friction, the radius of the journal, the clearance, delta T, and the pressure in PSI. And we can do this also in megapascal, yeah, in SI unit and in American or customer unit. Now, here we have a curve which is showing us, again, the Sommerfeld number with L over D curves, and then what is known as a dimensionless temperature rise variable. Now look at this variable. It is 0.12 delta Tc divided by P in megapascal. You may ask a question, how is this dimensionless? I mean, this one is in degrees Celsius, and this one is in megapascal. Well, that's what the 0.12 is for. So you can imagine that the 0.12 is actually having a unit which is megapascal per centigrade. And that's why this cancel out, and you end up with a dimensionless number. And here we have the same for delta TF in Fahrenheit, of course, divided by BSI. And that's why the conversion constant here is 9.7, which is different than 0.12. Now, what is important, ya shabab, is that Raimondi and Boyd, for all of their charts, gave us an interpolation function. That interpolation function can be used for any instant if you have a ratio L over D other than the one provided in the curve. I doubt that you will use this one. We will mostly stick to L over D, which is provided in the curve, but this is something good for design purposes. I think, ya shabab, I am going to stop here. This is where I stop with the other section. We have only 4 minutes left, and I think we'll continue the discussion, inshallah, next class.